The last real type of differentiation we'll look at is called logarithmic differentiation. So our motivating example would be to think of something like y equal to x to the x power. We don't really know how to take the derivative of this. All of our exponential rules need a number in the base and an x in the exponent, and all of our polynomial rules need an x in the base and a number in the exponent, but this time we have an x in both. So we're going to have to use a different form. And the idea is to start by taking the natural log of both sides. So now I have ln of y equal to ln of x to the x power. Properties of logs say I can move this x out front. And then I can do implicit differentiation. The derivative of ln of y would be 1 over y. And remember, when we're doing implicit, anytime we have a y, we need to multiply by y prime. On the right, we have a product rule. The first times the derivative of the second plus the derivative of the first times the second. So this is now y prime over y equal to 1 plus ln of x. Multiplying both sides by y gives me y times 1 plus ln x. And when we're dealing with logarithmic differentiation, we don't want to leave it like this. Instead, remember, y is equal to x to the x power. So I'm going to rewrite this as x to the x power 1 plus ln x. And this is the basic idea behind logarithmic differentiation. So let's look at a couple more examples. This time I have x cosine x. Once again, I have an x in the base and an x in the exponent. So I'm going to move to y and take the natural log of both sides. So ln of y is ln of x cosine x. Properties of logs let me bring that cosine down. So now I have cosine x ln x. The derivative of ln y is 1 over y times y prime. Product rule says cosine times the derivative of natural log plus the derivative of cosine, which is negative sine, times ln x. I can then multiply both sides by y. So now I have y times cosine x over x minus sine x ln x. And once again, I can change the y to, in this case, x cosine x times cosine x over x minus sine x ln x. In general, logarithmic differentiation is used whenever we have this x in the base and an x in the exponent. But it can be used on other things as well to help simplify them. Let's look at another example. Here I have a really complicated function that if I tried to take the derivative of, I would need to use the chain rule 3 times, the product rule once, and the quotient rule once, which is not ideal. So instead, we're going to start by taking the natural log of both sides. So ln of y is ln of this horrible function, 3x plus 7, square root of 2x minus 1, all over x plus 9, all squared. And now I can use properties of logs to simplify this a lot. This is ln. Well, first, let's deal with that exponent of 2. So 2 times ln of 3x plus 7 plus 1/2 ln of 2x minus 1 minus ln of x plus 9. When I take the derivative, on the left I have y prime over y. On the right, the derivative of the first thing would be 1 over 3x plus 7 times the derivative of the inside, which is 3. Keeping in mind we also do still have this 2 out front, so times 6. This is 1 over 2x plus 1, or 2x minus 1. The derivative of the inside would be 2 times 1/2 is 1 times this 2 is 2 minus 1 over x minus 9. The derivative of the inside there is 1, and then we need to multiply by this 2 out front. We can then multiply through by y. So I'm going to rewrite this. 6 over 3x plus 7 plus 2 over 2x plus 1, or 2x minus 1, minus 2 over x minus 9, all times y, which was 3x plus 7, square root of 2x minus 1, over x plus 9, all squared. So we had this really complicated thing that would take a lot of work, and using logarithmic differentiation, we can make it a little bit easier.